Right, so let's get started. This will be the second of the 5 or 6 seminars we'll have through the summer workshop. I'm happy to introduce today's speaker, Professor David Forsyth from the University of California at Berkeley. He started his academic career at Wits University in South Africa, then went on to Oxford, where he got an MA and a DPhil. And he, amongst other things, has been a Rhodes Scholar, a Fellow of Magdalen College. He's the editor of a couple of IEEE journals at least, I think.
Associate editor.
Associate editor.
Sent back the time for reviews.
And he has many honors and awards to his name. So without further ado.
Thank you.
Thank you. So I'm going to give now perhaps we could have a little bit less light at the front of the room. Is there a way to turn, because otherwise my slides will be difficult to read.
I don't know which one does it.
The board side.
Okay.
There we go. There we go. Looks a little bit better, and that'll be better still. Okay, so I'm going to talk about a variety of different projects, work done with a large cast of different people. It looks as though I'm running an empire, but actually what I'm really doing is benefiting by drawing slides from a large number of different loosely linked projects. There's work with Cobus Barnard, Pinar Dugaloo, Nando de Freitas, Manmartha, Tamara Miller, Alex Berg, J.T. Edwards, Ryan White, Michael Mayer, Yi Tay, Eric Leonard Miller, David Bly, Roger Bock, and David Ramanan, some of whom are students of mine, others ex-students, others colleagues. So the founding observation behind all of this is that there are very large numbers of really big collections of pictures out there. Many of these numbers are quite old. You can buy for small sums of money collections of 40 or 50,000 pictures. It's not that difficult to buy a collection of 100,000 pictures. Fine Arts Museum of San Francisco, with whom we've been working fairly closely, scanned about 83,000 objects and put their pictures online. You can search them with keywords. They're not that sorted on natural language, so one way to see all of the pictures is to search their collection on the word "the," which gives you everything back. CalFlora is a collection of pictures of California flowers. They got 20,000 images. Big collections include Hulton Getty. Now, my number for Hulton Getty is actually about 8 years old. 8 years ago, they had 40 million pictures. They've been collecting like mad, so they've got more. If you do a Google image crawl, you'll get evidence of hundreds of millions of pictures being out there. You can get satellite images with associated demographic information on the web. If you want to see what your house looked like in 1996 to a 1-meter resolution satellite, you just go to the web page and bang, there's a satellite picture. There's a gutload of medical images out there as well, rather than medial ones. And you may know that the BBC is releasing its video archive. We collected 500,000 news pictures with their captions by the simple expedient of writing a script that went to Yahoo's news pictures page and asked for everything with the word "the" in the caption every couple of hours. You run that for a year or so, and you've got more news pictures than you can shake a stick at. It's easy to get scanned medieval manuscripts, et cetera, et cetera, et cetera. So what one wants to do with this lot is to impose order. And it needs to be understood that there are relatively few current practical applications that are making money, but there are some. And the ones that are working right now, where people actually make money out of it, are essentially iconic matching. Is this picture that's exactly the same, up to a little bit of cropping, a little bit of scaling, and a little bit of other stuff, as other pictures? Now, some years ago, duty compelled me to spend 3 years on an NRC panel on the subject of pornography on the internet, which sounds interesting, but I can assure you it isn't. As a result of being on that panel, I learned about a bunch of applications that I would otherwise not learn about. One thing about people who take rude pictures is they tend to steal them from one another. And there's a significant market in managing copyright. There's an organization called BayTSP that basically, if you have pictures that you fear might be stolen, you go to them and you say, these are my pictures, here's some money, and then they crawl the web looking for iconic matches, and then when they find them, they send out rude letters as required by the Millennium Copyright Act, and you get some of the money and they get some of the money if the picture was stolen. Another application that's working right now and generating more a social good than money is certain classes of rude picture involve underage participants. And such pictures, it turns out, are actually quite uncommon. Now, there are basically two classes. One is pictures that were taken in the 70s, where prosecution is for possession. And the other is pictures that were taken recently, where there's not just a prosecution issue, but a social services issue. And it's very important for assorted prosecuting agencies to tell the difference. They want to know what they're dealing with, and they also want to be able to link prosecutions. How would you do that? You would have a very large library of such material, and you would try and make iconic matches of pictures and say, have I seen this before? Is it something I know that was taken in the 70s? Is it new? If it's new, can I see in the background, for example, furniture that I've seen in other pictures? Can I match that? And by so doing, link prosecutions and identify protagonists. This has been done successfully. There are a whole bunch of maybe applications where everybody sort of believes it's going to work and that it's a good idea, but there's not exactly real working money coming. One is web presence for museums. And I'll show you some examples of stuff where we've been able to organize a collection of museum artifacts in a way that you can browse them, and it's interesting to browse them, and you get some sense of what's there without being forced to do keyword searches. Another thing that a lot of people are putting money into trying to get working are various home picture and video applications. So the idea that manufacturers have is you might plug your digital camera in, and then once you've labeled your grandmother 3 times and children's birthday parties twice, then it'll organize all your pictures for you and label them and the like. That's kind of out of the reach of current technology, but there are a lot of people trying to get at that. The third application that a lot of people have been trying for is to say, well, in these very big collections, there are a small number of pictures that are worth a lot of money to, for example, newspapers. So the photograph of, let's see, a photograph of a presidential candidate meeting an unrespectable person might be worth a great deal of money. But there are a lot of pictures that might be worth small sums of money to people who want to use them to make their Christmas cards. And if you could build the right kind of interface, you might be able to connect the people who want them with the pictures that are there. They're certainly not going to prowl through 40 million images looking for something to put in the front of a Christmas card. There are some maybe searching applications. The one that I will put, I should have elevated beyond maybe because I think it's very significant, is one where you try to search scanned writing. And I'll show you a variety of examples of things that people can do and reasons you might want to do them. Another maybe searching application, we have obtained a very large number of photographs of insects within a museum collection associated with metadata. And what you might like to be able to do is the sort of traditional zoologist thing of prowling through a very large number of a very large number of insect specimens and noticing the one that's identified as species X is in completely the wrong place for species X. And either way, you get a paper out of it. Either it's not species X, but it's a new one, or it's species X turning up somewhere where species X has never been seen before. The record that people do this from might be 100 years old. Nonetheless, this is a sort of standard game in zoology. Now, the last thing I'm going to show you is that you could use these kind of collections to build a form of world knowledge. We'll show you a gazetteer of faces that we've built out of the news collection. Now, it turns out that search is well studied, even search within these picture collections. So what do you do with a collection of pictures? Well, the first thing you might do is try and index it on metadata. Keywords, the date of the photograph, the place. For example, the California Department of Water Resources has very strict rules for what photographers need to log when they take pictures. You may not know that the California Department of Water Resources generates an enormous number of photographs, but it does. And the photographers are supposed to log assorted things, and those are recorded as metadata, and you could index the pictures with that. Now, the problem, of course, is the photographers don't do what they're supposed to do. So it's not as helpful as you might think. The next line of research was to do a form of content-based retrieval. So you would try and generate some interpretation of the picture and query on that. And the usual thing is to query by example. So you say, I would like a picture that looks like this picture. What do we mean by looks like? Well, the early thing to do was things like color histograms. Has the same collection of colors as. There's quite a long line of work on this, including, as I say, various entire conferences. You might look at local features in the picture. You might look for particular bits of color or shape. Another line of work that's had a fair amount of work in it. And you might even allow people to do relevance feedback things. So I search for a picture that looks like this. I get a pool of pictures back. I say, I like this one, this one, this one, but not that one. I try again, and some enormously smart supervised learning thing inside the box has said, oh, well, let's rearrange the resulting pictures. Bang, they come back, and with any luck, it looks better. That's been studied. It's not a tremendous success, but people have tried it. The other thing you could do is to sort of query by class. I want a particular type of picture. There's been a fair amount of work on what I persist, despite various people trying to dissuade me, in calling naughty pictures. I did a little bit of it, and then Wang and Chan have done this, mainly because there are now 4 or 5 products out there that all claim to be the first thing that can look at a picture and tell you whether there's something alarming in it. The summary here is that it doesn't work very well, but a lot of people care. The problem is that although search has been well studied, there's a huge gap between what search can do in pictures and what people will actually pay for. So a lot is known about what people who index and use movie collections do. There's work by Enser and McGregor, Orniger, Armitage and Enser, Marculo and Simon and Olivia Frost, etc. What you do basically is you go to an image archive, you watch the people who retrieve pictures, you look at the queries that come, and you try and find out what people actually do. And typically somebody phones up and says, I want a picture like this, and you chat to the archivist, and the archivist says, oh, I know, there's one of those in filing cabinet 23. They go over, they fiddle through, they bring it out. The kind of queries you find in the log are really not queries that are accessible to computer vision at present. So this has taken, Enser and McGregor have a long list of these things. I took some of them, but it's really startling reading. Smoking of kippers, the depiction of vanity in painting, cheetahs running on a greyhound course in Haringey in 1932. These are things you can't do with color histograms. The real operating question in the background here is, what is this about? I got a picture, I got some associated metadata, I got some other stuff, and I need to know what it's about. That needs some form of recognition. Now, we can't do object recognition, but we have this nice payoff. We may very well be able to live with dubious accuracy because there's no other alternative. And it has to operate on a large scale. Both of those are interesting constraints. There is other information associated with pictures, captions, metadata, and what I refer to as coherence. Bits of an object in a picture look like one another, but not like other objects, or at least sometimes. So there's a remarkable phenomenon that one notices, which is that annotation typically results in complementary information in the words and in the picture. So if I go to one of these systems, this is somewhat iconic as a representation of what's returned, but I can go to Berkeley's Blob World system and I can query for pictures that are annotated with the word rose, and I'll get roses, but I'll also get rose beetles, a rose cathedral, and in the following page I would get a roseate spoonbill. So all sorts of odds and sods get the word rose. If instead I query for a big red blob in the middle of the picture, and that sort of indicates how I might query for a big red blob in the middle of the picture, I'm going to get roses, but I also get Scotsmen and stop signs and golfers and various other bits and pieces. If I do the absolutely obvious thing, which is to query on the union of those two, the intersection of those two, the word rose and a big red blob, lo and behold, I get lots of big red blobby roses. Right? Why? Because annotators might very well say there's a rose in the picture, something that's really hard to do with computer vision, but they're unlikely to say it's a big red rose bang in the center of the picture because it's obvious when you look at it. And we can do that big red thing in the middle of the image. So this complementary information is powerful. So I'm going to show you a variety of ways of exploiting this complementary information. First thing we're going to do is build a probability model linking images and annotations, and then we'll exploit various co-occurrence properties, and that'll give us forms of search, illustration, and annotation. And then we'll predict words from regions, and we'll link faces with names. So browsing. Searching, it turns out, is hard. And I always use this example of an unfamiliar bookshop. If you walk into an unfamiliar bookshop, you do not usually go to the person behind the counter and say, I want this, this, and this. Why do you not? Because there may be no prospect at all of getting a sensible answer, because it might be a bookshop about something completely different. It's easier to search when you know that what you're searching for is likely to be in there, and you have some sense of what you're searching. Instead, if you really don't know what you're dealing with, you are likely to browse. You'll probably go to the bookshop and kind of poke around on the shelves a little bit before bothering the person behind the counter. That rather intuitive story is actually supported by real user studies. Naive users, people who don't know collections, tend to like to browse them. The problem with browsing is that it requires organization. If I go to this putative bookshop and I say, I'm going to browse it, and the owner is an eccentric who has organized his books in numerical order of ISBN, the browsing exercise is completely unhelpful. It's got to be organized in a sensible way. Those of you who've used Foyle's Bookshop in London, where the books are organized by publisher, will have a clear sense of how hard it can be to browse badly organized books. It's generally an underrated problem. It doesn't look terribly sexy to people to organize collections to make them browsable. And there hasn't been a lot of work. There has been some. Every time I give this talk, I draw it to people's attention because I think there's room for a lot more. So what are we going to do? We're going to cluster words and pictures, and then we're going to lay out and browse the clusters. And the nice thing about clustering, of course, is if I've got a really big collection, instead of showing the whole cluster, which might be hard, I could show representatives of each cluster, and I could browse the representatives and then drill down into the cluster. And I'm going to build those clusters by building a joint probability model, linking the words and pictures, and we'll use Hoffman's hierarchical aspect model. It came out in Hoffman and Pachika. I'll give you a quick sense of how it works in a second. So what we're going to do is take the picture, segment it. There are all sorts of segmenters out there. Later on, I'll show that I can suborn this exercise to score the goodness of segmenters. But right now, we'll just take the picture and segment it. And we'll take each segment, if they're big enough, and we'll attach the region size, position, color, a bunch of texture filters, and some really simple shape features to it. Then what I'm also going to do is take any annotation and basically rip out the nouns. The simplest annotated collections are annotated only with nouns anyhow, which makes life easier. More complicated annotations have actual language in them. Right now, we did parts of speech. We preferred nouns only. We pushed things through WordNet, although it didn't make all that much difference. And we did sense disambiguation because it was helpful. Again, just used online stuff for that. There was nothing special. So how does Hoffman and Pachika's model work? Well, what I'm going to do is I'm going to think about the world as consisting of a bunch of sort of lumps of probability. And we've drawn the lumps of probability over here as triangles. And a lump of probability can fire off two kinds of thing. It can fire off image features, a vector of those image features as described, or it can fire out words. And now what I have is a set of clusters of images encoded as leaves of a tree. So the way I get the images in this cluster is I go to the top one on the path to the root, and I fire out some image stuff and some words, and then I'm going to go to this one, and I fire out some image stuff and some words, and then I go to that one and fire out some image stuff and some words. And the hope here is the kinds of image stuff and words that are shared by very large numbers of images gets fired out at the top, and the stuff that's specific to one particular class gets fired out at the bottom. How would I fit a model of this form? As you can see, with pretty much anything of this form, at the end of the day, it turns into EM. It's a sort of straightforward missing data problem. The missing data is the path and the nodes that generated each data element. I'm going to do EM. If I knew what the path and node were for each data element, then it's easy to get a maximum likelihood estimate of the parameters. If I know what the parameters are, I can figure out the path and the node, and the whole hideous panoply creaks into... So now what are we going to do? Well, we'll take this stuff and we'll apply it to about 8,000 pictures taken from the 83,000 from the Fine Arts Museum of San Francisco and cluster that lot. And that collection looks a little bit like this. You get a digital image of an object, and as you'll see in a second, these objects could be prints or paintings, but they could also be photographs of statuary or all sorts of other things. You get web numbers, you get a description, a title, a primary class, display date, country, artist, that sort of thing. The description is typed in by volunteers. And this description was prepared for completely different reasons. The museum prepared the descriptions. Some of the volunteers give you just an account of what's in the pictures. Others tell you how they make it how it makes them feel. All sorts of random things appear in these descriptions. Now, with a little bit of luck, we will get out of this, and I'll actually show you the browsing system. Where did it go? Here we are. So what one does is do the clustering that I described, and then for each cluster, pull out one image as being representative of the cluster. Now what I can then do is say, I know the, I've forgotten the name, the usual probability distance between the clusters, and I can lay them out using multidimensional scaling? Sorry, again, words just disappear occasionally. I lay them out using multidimensional scaling, and I stick them into a geographic information system, which we happen to have lying around, a GIS browser, and now I can browse them. And what I can see here as a display is a whole bunch of little pictures, each little picture representing a cluster, and then over there, something that tells me roughly where in the pool of clusters I am. So there are lots of pictures that are a little bit like that, and then there's some pictures or clusters lying out. I can zoom in a bit to get a better view of those pictures, and then we'll go and look at good clusters and bad ones in a second. So let's take a look at this and see what's in its cluster. Lo and behold, a whole bunch of other ornamental plates, and nothing's perfect, so a couple of rather randomly placed prints. I can then, having laid everything out, go and click on a particular plate, and with the speed of the web, we go zinging over to the Fine Arts Museum of San Francisco, who in fact have that plate, inscribed plate, and we can look at it in greater detail and poke around in their records and stuff. Time doesn't allow lots of browsing here. I'll show a couple more clusters. You'll understand that the nature of things is that I tend to show the better clusters when I can. This one I'd remembered as being a good cluster, but actually that print of Mount Fuji seems a bit iffy in with the vases. But it's on the web, and I assume somebody will want the slides, and in the slides is the URL. So it's relative, and you see, we have, that looks like a ceramic swan, if anything. We've got random bits of ceramics together. Now, why did a whole bunch of bits of ceramics that don't look like one another end up together? Well, the annotations probably did look like one another. Equally, if we go and look typically amongst the drawings, there's a good one. Fairly decent example, not the best I could have shown, I fear. But if we go and look amongst the drawings and watercolor washes, you will tend to get things that end up together because they look like one another. So now I have something that summarizes this information and makes it roughly browsable. It's very difficult indeed to tell whether something of this form is a success because it involves things like user studies and the like, which are a nuisance to do. However, what we can do is look at other things. Now, there's several things I can do when I've got a probability model linking words and pictures. The first thing I can do is search. I can ask, I want documents that have high conditional probability condition on the query items. And of course, because I can link words and bits of pictures, I can link on water, sky, cloud, and a big orange blob. There's a tradition in image retrieval of looking for sunsets because they're usually fairly easy to find with color histograms. So we followed the tradition, and lo and behold, one gets a reasonable result. Can you really evaluate search? Not really, but there are other things you could do. There are other ways to search on annotation. Actually, that slide is in the wrong place. That was a mistake. One could search purely on the annotations. So what actually, no, I'm not going to talk about that slide. I'll come back to it. So the other thing I could do is try and predict pictures from words. I've got a joint probability model linking words and images. I could say, give me an image with high probability given the words. And I could take text passages. What we did was we went out and found a whole bunch of 19th century novels, text passage from Moby Dick, push it through our language processing. You'll notice that not all of these nouns are in fact nouns. So our language processing is a little bit marginal. Push it through the language processing, and then say, basically give me pictures with high probability given those words. And lo and behold, what one gets back is a bunch of pictures, including lots of pictures of people in boats, and in fact, some people in boats chasing whales. So it's a reasonable pool of illustrations from which to work to illustrate a passage like that. The next thing I could do would be to try and predict words from pictures. Right? So I predicted pictures from words, but actually what I'd like to do is predict words from pictures. Now there's an obstacle to doing that, which is that Hoffman's model uses document-specific level probabilities, meaning that it only works for pictures that you actually used in the learning set, and that's not terribly helpful. What I really want to do is predict words from pictures that I didn't actually learn to predict words from pictures with. You can dodge this by smoothing empirically. The details of the smoothing don't seem to matter very much. There are a variety of ways of smoothing. But the attraction of actually predicting words from pictures is several. One is it's easy to score. The other is it allows large-scale performance measures. And the performance measures might look like predict words from pictures for which you know the words, and then see whether your predictions line up with the words that you know. And of course, it allows search using keywords on pictures that were not in fact annotated. That was the slide I showed back, and we'll go back to it. So what happens when I do this? Here's a picture. It's been segmented. From the picture actually came with these light blue keywords: grass, tiger, cat, and forest. The words that are actually predicted using this pool of regions are tiger, cat, grass, people, water, Bengal. And then you can see the prior beginning to punch through: buildings, ocean, forest, and reef. Here, picture, segments. Words that actually came with it were hippo, bull, mouth, and walk. This is from the Carrel collection, where you just get a set of annotating keywords. The predicted words were water, hippos, rhino, river, grass, reflection. Something I wish I could claim as a triumph for physical models in computer vision, but is actually just pure good luck. Why? Because there actually is a reflection in the water, and it appears in the segmentation. But this is pure dumb luck. There's no other way to. One-horned. Why do we get one-horned? Well, rhino. It doesn't always work terribly well. So we have a picture that flower, coral, berry, leaves, and plant, and we predict fish, reef, church, wall, people, river, etc. Now, there are a lot of things you could do with these predicted words. And one thing you could do would be you could take the picture, rack up some predicted words, and then do keyword searches for pictures. So if you indulge my disorder for another second, that's what this is about. This is Manmartha's work, Feng, Manmartha, and Lavrenko. But basically what I'm going to do is now build a slightly different annotation model. In fact, a significantly different annotation model. I'll build a joint of words and image features by mixing over all the training samples. And then I can annotate, and then I have a likelihood model to query, and lo and behold, the queries turn out to be work rather well. So I take my picture, I predict words from the picture, then I rack up the picture and I do keyword searches. Here what we've done, what Manmartha and them have done is outdoors, sky, transportation queries, and back come automatically annotated pictures. A reasonable response to the query. Okay. There's several other things you could do here. One is it's really easy to score the words predicted. I showed you how. The picture came with some words, we predicted some words, you figure out which is which. What that means in turn is you can score image segmenters. You can say, I prefer the segmenter that gives me better word predictions when it's racked up in a model like this. And it turns out that different segmenters give you different levels of performance. I don't want to go into this slide in great detail, but basically, bigger is better. Blob world is one kind of segmenter. NCUTS is another kind of segmenter. You will notice that persistently, for different kinds of data, NCUTS outperforms blob world. These funny little vertical bars are things that you don't often see in vision talks. They're known as error bars. Why can we put error bars in? Well, we've got thousands of pictures. We can do basically a bootstrap estimate of the error. So we really know that one segmenter is a very great deal better than the other. Okay, there's a variety of things that are open here. One is one would want to package up the software for clustering and drop it on various museums to see what happened. That's something that's on the go. Experiment with other image representations, segmentation, fusing, word fusing, etc. Better layout in the browser, better understanding of how well search on annotation works, annotation with people's names, that kind of thing. Okay, here's the next thing. We're now going to go on and predict words from individual image regions rather than whole images. And we'll end up with something that draws a kind of parallel between building a lexicon and doing object recognition. So the problem with the annotation that I talked about was I took the picture and I predicted some words. But I didn't explicitly encode a correspondence between the words and the bits of picture. Now that's a mistake. It's natural that this one should attract tiger and cat, and that should attract grass. And what I'd like to do is preserve that correspondence. So how might we do that? Well, one thing to notice is that you could see a strong analogy with the process of building lexicons using statistics. So what I could say is, if I rack up, the Canadian government is sort of the general target here. The Canadian parliamentarians have that habit that other parliamentarians have of talking a great deal, but what they say is written down both in French and in English. And you know that the French is the same as the English, so now I have bazillions of words of French that mean exactly the same thing and are aligned with bazillions of words of English. So then what I can try and do is figure out which English word goes with which French word. And I have a problem that looks a little bit like this. I've got some English words up here, I've got some French words down there, and I've got a missing correspondence. Right? But in fact, I've got millions of short chunks of English and short chunks of French with missing correspondences. If I knew what the correspondence was, the lexicon would be easy. If I knew the lexicon, the correspondence would be easy. Bingo, that's EM. And we can set it up and pile in with EM. And there are all sorts of cute things you can do to build a more complicated model. That rather looks like the problem that we have on the vision side, which is I've got some bits of picture over here represented one way or another, and I got some words that have got omitted over there, and I want to build a correspondence between the bits of picture and the word. I want to build a lexicon that says this kind of piece of picture fires out the word sea, and that one fires out the word sun. And there are some caveats here, but one can do it. So the first thing is to segment the image, and then take those segments, represent them with one or another image representation. In fact, we used the one that I described a little earlier, color, texture, a bunch of stuff like that. Then what I'm going to do is vector quantize those regions. And that means, for example, this region attracts the tag 390 because it's in cluster 390, as does that one, as does that one. So 390 is sort of big plain blue ones. This is 214, that's 448. You can't really expect all grass patches to have the same number. Big green swirly textured ones. Now my data set begins to look like this whole English-French thing. I've got a bunch of basically numbers over here, and I've got a bunch of words down there. And what I want to do is to come up with a lexicon, joint probability model. These kinds generate the word sun. These kinds generate the word sky. And these kinds generate the word horse. You should look at this with a degree of suspicion. By the way, I could regard this, I've fudged on this issue, I could regard this either as a conditional probability table or a joint probability table, and there are applications for both. In a conditional probability table, I really am trying to do object recognition, independent of the statistics of the training data. In the joint probability table, I'm going to be trying to do well at the things that turn up commonly in the training data. Why do we have grass in the horse? Well, it turns out we have large numbers of pictures of horses with grass in the background. We never see a horse without grass. And that means there's an underlying symmetry in the training likelihood. You could flip horse and grass and do about as well. And that symmetry is something that remains a matter of interest. It's difficult to get rid of if you've got it. So I build one of these tables. We estimate using sort of traditional methods a model. We go out and label pictures. Some pictures get labeled very well indeed. So sky, tree, tree, sky, 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 snow, that's a little iffy. The tree over here is a little bit iffy. Buildings over there is satisfactory. Water is iffy. Sky is legit. Rocks iffy. People entirely satisfactory. Sky satisfactory. You'll notice that we tend to be looking at stuff rather than things here. People en masse rather than a person. Water, sky, rather than tiger and bush. Doesn't always work. So the reason the elephant has the buildings on its nose is that it's actually quite difficult when you've got a segmented piece like this to predict an elephant from just one ear. Right? It looks like all sorts of other things. What one should do is unify these regions in some way and then predict according to the whole thing. This is one of the great difficult tricks of computer vision. We'd do it if we knew how to do it. It still remains fairly hard to do. However, one can score how well one does. Right? Now, scoring has the two ways you could score. One thing you could do would be you could look at a picture and say the word grass is in the right place, the word tiger's in the right place, the word cat's in the right place, the buildings are not in fact there, there are no mares down here. The problem with that is it's very hard to do in large volume. Right? So the alternative thing you could do would be to set up a proxy which says drop the correspondence and score as an annotation. Now, if I do that, I cannot score the quality of my correspondence. I'm going to have to go back and do a bunch of them by hand. But what I can do is argue that if for a very large number of images, I am able to get the annotations right, then the only way I could get the annotations right and the correspondence wrong would be if there were symmetries in the data set in the first place. Right? So what I'm going to do is I'm going to do this as a proxy on large scale, and then by hand I'm going to go back and score some of those. If we do that, what I can score by saying, look, pretend I annotated the picture with the predicted annotation words, and then I did keyword retrieval, and I know what the keywords actually are because I know what words are associated with the picture. What would the precision and recall of my keyword retrieval be? You'll notice that for some words I do rather well. Basically, 0 precision, 0 recall is down here, and you'll notice a sort of suspicious cluster of words down there. There's some things where we basically just don't have a clue. Up here, which is the good place to be, there are some words. We'd like to be up there, but we can't. But cat, swimmers, polar, mare, pillow, horses, sky, water, people, foals, we're talking about words that are reasonably acceptable. Now, the next thing that I can do is say, given that I predict a word, and I predict it correctly, it really should be there, did I put it in the right place or not? And I can score that by hand. I can go back to the words and I can say, what is the probability of it being in the right place? So this is the probability of the correct prediction. That's the word. If I predict the word plants, for 60% of the time, it's in the right place. Town, 50% of the time. Sun, 45% of the time. And it falls off after that. People, relatively seldom. Okay. Now, there's some advantages of thinking about recognition like this. One of them is that I can let my data sets determine what I try to recognize. The second is I can try to think about recognition on a large scale. Now, this correspondence problem turns up in other places as well. And the one place I want to show you is word spotting. Now, previously what I did was I took image regions and I lined them up in correspondence with annotations. What I might do instead is take handwritten words, try and segment individual words or letters or whatever, and line up those objects with text. And if I could do that, then I could do search on handwritten documents. The person who's sort of led this game is Manmartha. There is a tremendous quantity of handwritten documents out there, a lot of which is scanned. So large quantities of medieval Latin documents have been scanned. We've got huge quantities of field notes of biologists who went around shooting wildlife in California in the early 20th century that have been scanned. Manmartha's been working with George Washington's orders that have been scanned. And what you can do when you do this is you make the document searchable with free text ASCII. So I could type in provision or whatever, and lo and behold, I find the bits of the document where that appears. So we'll do a brief demonstration of that as well. Whoops, if we can get the, there we go. So this is Manmartha's demo, and I'm afraid I canned a query because I wanted to be sure it was there. If you search George Washington's orders for the word incarnadine, you're going to end up in trouble. But if you use something like the word sergeant, which he uses rather a lot, at the speed of the web, the weather must have hit the, there we go, bingo. What we're going to get back down at the bottom of the page is a series of lines where Washington has written the word sergeant in his orders, and we can get the page from the written orders as well with the word sergeant lined out. Now, you should see the utility of this general notion, which is that there is copious quantities of scanned handwritten stuff out there. It's not worth transcribing. But if you're a serious historian, you'd like to know if there was good stuff in it and what the good stuff was, and the way to do that is to be able to search. I've gotten a little into this game as well. I take a slightly different approach from Manmatha. Manmatha has been saying, think about words as the pictures, think about the handwritten words as the pictures and the aligned words as the text, and predict an annotation. I've been thinking of handwriting as a substitution cipher. One finds lines with elementary methods, uses vertical bars to quantize direction, and then I model the text with a generalized HMM, basically saying blocks of text, individual words could generate large quantities of vertical bars or small quantities of vertical bars. I can use dynamic programming on that. I have to use letters as a word representation. Why? Because I'm using Latin. Latin is an inflected language, which means the form that you see of a word may occur very seldom in a document. You can't think about the language as being made up of whole words because then there are too many words. I use one example glyph per letter, which means a total of 22 examples. It's naughty because it should be unsupervised, but you can get quite good searches. Now, if you look over here, this is a search on a medieval document. This is a handwritten version of Terence, and we search for the word MIHI, which appears in the editor's transcription of this document rather often. And when you look at this, you should think, why is he making all this fuss? Because the search clearly doesn't work. And the answer is it does work. This particular scribe always spells MIHI, MICHI. And the editor, when transcribing the document, drops that extra C as being a weird medieval emendation of no particular significance when preparing a reference version of Terence. If I search on MIHI, because there isn't one, I get rather random results. If I search on MICHI, lo and behold, I get it. That means that I can think about this document as being something that I can search with ASCII text. And I actually see the ink in the document as opposed to what the editor wrote down. And that may be very significant for a scholar of paleography. There's an awful lot to do here. One wants to compare models of word prediction, the extent that different models work, how well they work, etc. There's a huge chunk of data on different models in a JMLR paper by Corbus Barnard and some others. David Blay and Michael Jordan have built another model which seems to outperform it. We used a really crude image representation. There are tons of image representations you could use. We're a bit iffy on questions of vocabulary management. There are questions of the effective supervision. So I spoke about these symmetries in the data set. Now it's clear that that symmetry could be broken by a very small quantity of supervisory information. If I said that was the grass and this is the mare, the symmetry would be gone. Also, words aren't independent, so several people have benefited from that observation. Now, the last thing I'm going to show you is a process of linking face images with names. It's an important special case for several reasons. Vision is very good at detecting faces. There are tons of faces out there, and there are a whole bunch of sort of mildly creepy three-letter agencies who want to know an awful lot about people's faces. There's a little bit of wishful thinking in some of it, but faces are really interesting. The other thing that's nice about faces is you should know, anybody who's read the newspapers knows that there are claims of performance of face recognition that are not borne out in practice. Why? Probably because most of the data sets that have been prepared in laboratories are not really pictures of faces in the wild. But if you think about the news, it's actually a data set on a pretty epic scale of faces in the wild, what people actually look like when photographers go and take pictures. And it will turn out that lining up faces with names is somewhat easier than recognition. So our news data set involves about 500,000 news pictures with their captions. We sucked them out of Yahoo over about 18 months. The news consists almost entirely of people. They're either politicians, actors, or sports players, but it's a distribution with really long tails. So there are a small number of people who appear really often. We've got pictures of George Bush doing anything conceivable he can do with his face because he's always photographed and we get them. But there are also people who turn up very seldom. And we have a sort of fairly basic correspondence problem here with some interesting little twitches. So there's the President and the Defense Secretary. You'll notice that any reasonable named entity recognizer passed over this. Ours is not great. We homebrewed one that wasn't satisfactory, and we've passed to a somewhat better one, which isn't reflected in the slides yet. So drop the W. Bush and President George. I've got three names there. The President's name, the Defense Secretary's name, and Saddam Hussein. Now, Saddam Hussein is not in the picture. Okay? I got two faces, and I've got to figure out which of those three names the two faces attract. And that's my correspondence problem. The thing that's fun about this is we get tons of pictures of him, but he doesn't turn up all that often. This is an Israeli doctor who removed the fork from the thorax of someone who swallowed it while trying to get a fly that flew into her mouth. That doesn't happen very often. It usually doesn't happen to the same person or the same doctor. So you can be pretty confident that we've got one picture of this guy, and he disappears into the wastes of history after that. So here's the process we do. We take our pictures, extract proper names with currently a rather crude name detector. I'm not talking about it in any detail because it's a bit crude. We detect faces with Cordelia Schmidt's face detector, and from that 500,000 pictures, we said we're going to take the biggest face detector responses. There's no reason to fool around with marginal faces when you're getting started. And the very big faces, we get 44,000 very big face detector responses. So then what I'm going to do is rectify the faces. And by that I mean I'm going to take the eyes, nose, and mouth, apply an affine transformation so they end up in the right place. One doesn't mark the eyes, nose, and mouth in 44,000 face pictures by hand. So we built something to do that automatically. When they're properly rectified, I can tell of these, about 34,000 are properly rectified. I'm going to kernel PCA the rectified faces and estimate linear discriminants on that. Very crude representation, but fairly satisfactory in practice. Now each picture and its caption turns into a data item that looks like a bunch of face vectors describing the instances of faces and a bunch of names. And I've got 27,000 of those for k less than 4, i.e. 4 or fewer names in the captions. What I'm now going to do is, having taken those linear discriminants, basically break the correspondence with a modified k-means. You can see what I mean by modified k-means is I'm going to assign faces to the face cluster of those named that is closest to that face in the linear discriminants. Then I'll recompute the centers of the clusters and iterate and just keep going with distance in the linear discriminant space. Then I'll recompute the discriminants, recluster, keep going till it settles down. This is crude, but it's remarkably effective. Simple examples. It's fun to put the face detector response and the name underneath it. You'll notice over here, by the way, there's more than one name in this. Claudia Schiffer, it's clearly not Matthew Vaughan, or for that matter, Braunschweig. There's Bush, Powell, we've got them right. There's Kate Winslet and Sam Mendes. So one can do a couple of other things. There is a trade-off between size and accuracy here. So we can take a likelihood model and go to these clusters and look for outliers in the clusters. And I can say either you're going to have more examples, which are going to be somewhat ropier, which would be this case, or I could have fewer examples that would be much more accurate. The second thing I could do is merge faces with somewhat different names. The thing is that it might be tricky to tell that Venezuelan President Chavez and Hugo Chavez are the same guy, but since they have the same face, which is obvious, I can fuse the clusters, and that's going to help me. So we get out of this 2 dictionaries, I think I'll show one of the 2 dictionaries given time, which basically just contain face examples for very large numbers of people. I'll show you the clean one because I prefer it. So the first thing to look at here, let's get this page down to a reasonable size. The first thing to look at is the number of people whose faces we've observed. I'll show you all the funny, or some of the funny errors. There are a variety of them. Now, it isn't resizing the layout, but you should get some sense of how many individual people we have entries for from this process. Right? There are lots and lots and lots of people in the news. You saw the error where somebody's tummy was recorded as a face detector response. I think there are about 1,000 individuals here. Let me show you one of the congenial things. There's a political joke here for anyone who wants it. So this is one of the clusters we have of the current president. You'll notice that the correspondence process isn't perfect. So this puzzled-looking fellow with the mustache is some form of bodyguard who turns up behind him occasionally. But that is a mask worn by a political demonstrator to make one or another point. There are other things you should notice is the extent to which his color changes and which is expression changes in being photographed. So here's a sort of deep yellow color over here. You'll see pale purple, this funny red, that rather pale gray color. It's a phenomenon that's not much noticed, but face colors change a lot in news pictures. Let's see, we can go to a couple of these photos. The other thing that's nice about this is people do, when they're being photographed by news photographers, the most extraordinary things with their faces. There's a sort of pant-hoot expression down here somewhere that is usually seen as being rather funny. It's towards the end. You'll see how many examples of this fellow's face we have. You'll see that purple face in the middle of the page has to do with a political demonstration poster. Down here is a photograph you could reasonably believe that the minder's wish hadn't been published because of the pant-hoot expression. The photograph comes with its caption. We've got 400. These are the clean things. We've got 400. In the somewhat dirtier cluster, we've got many thousands. So there's the prospect of building a non-parametric face model for some individuals and possibly building even animations. I want to show you one of the kind of things that can go wrong, which is one of the reasons this web page we don't publicize much, because when they do go wrong, they go catastrophically wrong and are capable of causing offense. Let's go up here. Now, what is going on there, you could reasonably ask. Why is that person called Adolf Hitler? And the answer is the following. This is Hertog Dabler Gemelin, who compared the sitting president with Adolf Hitler. We don't have a picture of Adolf Hitler. We know she's not George Bush. And we missed in the name detector her name. Right? As a result, if that's not George Bush, it's got to be Adolf Hitler, and we've got a problem. Okay? So this kind of correspondence reasoning has limits. Nonetheless, one can take it somewhat further than we've taken it. Well, we have taken it somewhat further. It turns out you can figure out how well it works, and it works rather well depending on how many clusters you have. So what I'm going to do is just make a record of the frequency that an image drawn randomly from a cluster is not in fact a picture of the person named in that cluster. So if I have very large numbers of pictures and very large numbers of clusters, i.e. I don't do the pruning thing, the error rate is quite large. As I do the pruning thing a little bit, I can end up with a relatively low error rate. This compares very well with the best laboratory face detection under the best circumstances, and you'll have seen from our pictures that there are wide variations in expression, face coloration, spectacles, moustaches. We've got one unfortunate fellow wearing an obvious wig, et cetera, et cetera. So these are quite good numbers. You can also ask how many bits are required to fix the result, and that gives some insight as well. What I want to do here is to point out that what I showed you was working, but we're actually missing language cues. So if you look at this caption, quite obviously, from the caption, without looking at the picture, Sahar Aziz is in the picture, Jason Treesh is not in the picture, Bill Allison is in the picture, and Jim Harrington is in the picture. This is a language thing. Right? You can read the caption and say who's in the picture. So what we should be doing is building some language thing that says, this one's in the picture, this one's in the picture, this one's in the picture, that one is not, and thereby simplifying the correspondence process. And it turns out you can do that. So in some sense, it's a really simple thing conceptually. If I build the thing I've described, I now have a very large number of faces linked to their names. Because I've got faces linked to their names, I've got what you can think of as supervised training data for something that will say, this one's in the picture, this one isn't, and I can train that and go backwards. The respectable thing to do with that observation is to turn it inevitably into EM over the correspondences. I'll build a little generative model that says the way I get pictures like this is I generate a bunch of names with some language context around them. Then for each of these names, I generate a bit. And that bit is in or out, in the picture or out of the picture. And the ones that are in the picture generate faces, and then a whole bunch of other faces turn up randomly in the picture. Now what I'm going to do is basically estimate this, which is, if you like, P of this bit given that lot from that data set. And I can do that by noticing that there are a pool of available correspondences. So in this picture, I get two faces, and I get two names, John Furlong and Winter Olympics, and there's a relatively small set of correspondence possibilities. Name 1 goes to face 1, name 2 goes to face 2. They're swapped. Name 1 generates face 2, name 2 generates null, etc. And from these, I can estimate the probabilities and fit a model. We use a very simple model at present. It just assumes that the language context is conditionally independent given the bit, and then we do the whole Bayes thing and turn it around. Language significantly improves naming. So what I'm doing here is showing you a bunch of faces where I show the name attached to the face in the original pass, where we didn't use the language at all, and then once the EM associated with the language has settled down. So this face used to be named CEO Summit, but when we attach the language module, we've reduced the correspondence ambiguity and it's named Martha Stewart. It used to be named US Joint, named null. My favorite, put here entirely by accident, but I'm rather fond of it nonetheless, is used to be named James Bond, now named Pierce Brosnan. Okay? Now that's right. What's actually happening here? What's happening is in these captions, there's a strong bias to put the name of the big face in the picture first in the caption. You can build quite a good named entity recognizer by just looking at the first couple of words of the caption, because it's almost always a name. And the thing is that this caption actually starts with Pierce Brosnan, and then later on it says James Bond. And we don't know which is which. But once you've got a little bit of language context, you can say, well, if you've got two names in the caption and only one face, the one that's depicted is the first. And that gets us this. There are a bunch of other congenial, this fellow got elevated in official responsibility by our name thing, etc. So then you can ask, does it make a difference? And in fact, it makes a very big difference. How do you tell whether it makes a difference? What I'm going to do is I'm going to rack up 1,000 faces. I'm going to attach the correct names to them. And then I'm going to say with what probability or what percentage of them turned up in the right cluster. If I proceed without a language model, ignore for the moment the distinction between these two columns. If I proceed without a language model, the answer is basically based on appearance somewhere between 50 and 60%. If I attach a language model, I'm going to go from the high 50s to the low 70s in this case, and from the mid 60s to the high 60s to the high 70s in this case. It's a big difference. Okay. What's the difference between these two columns? Well, there are two things you could do with a bunch of correspondence missing variables. One thing you could do is do EM, which is compute the expected correspondence conditioned on your parameters. The other thing you could do is take the best correspondence conditioned on your parameters and ignore the others. Statisticians regard the second procedure with open revulsion. It's known in the vision community that for many kinds of vision correspondence problem, this procedure gives you a much better answer than that one for reasons that are somewhat mysterious. So this turns up in the structure from motion community and in a bunch of other places, and it's turned up over here. So it's a sort of nasty little phenomenon that we don't fully understand. It may have to do with averaging in things that don't belong in the average and getting noise in. It may have to do with the fact that the asymptotics aren't quite what they think we are. We're not really sure what it is. You get better clusters too. So if we proceed to build a face dictionary without this language model that I've described to you, then the clusters, for some example clusters look like this. You'll notice there's a cluster here named US Open. Named entity recognizer isn't that bright. It thinks that the US Open is the name of a person. There's some faces knocking around, bang, we're okay. The minute we start looking at where the name turns up in the caption, the name US Open persistently is not depicted. If it's not depicted, it doesn't get any faces and we're fine. Elizabeth Dole, we get rather more examples of Elizabeth Dole. Why? Because previously, when we had slightly more correspondence ambiguity, she occasionally turned up in the wrong cluster. Because we've knocked out some of those alternatives in the captions, we get more pictures in the right place. So it's generally a good thing. And we get a cutesy little natural language processing module for free as well. What have we done? We built something that can take a caption and say, this person is in and that person is out, just by looking at the language in the caption. That's the whole point of the EM training procedure. And lo and behold, it works rather well. So here's a caption. We've taken the name and written in in front and behind of the name, just to indicate who we think is in and out. Pete Sampras is in, Christian Pless is out, the US Open is out. Gerhard Schroeder is in, Jacques Chirac is in, everybody else is out. Pamela Reed is in, Veronica Cartwright is in, Philip Kaufman is out. This one, by the way, is wrong. Okay, it's not that easy to tell. You've got to read the whole caption, but it's wrong. Okay, Stephen Joseph out, comma, shown above. Right? Our language model wasn't smart enough. We did not, in fact, look for the small number of obvious words like shown, depicted, etc. And by not looking for them, we missed that. But it turns out, again, you can score something like this very easily. If you build a baseline which just says every name is in, then the number of in-out labels you get correct is about 60%. About 60% of the names actually are in. If you take my EM labeling and you take the model that results, I can get about 76% of the labels correct. So that's a real improvement. And if I do this maximum over correspondences instead of expectation over correspondences model, I can get about 85% of the labels right. So I really can tell who's in the caption for a large number of cases, and it really helps. So what does one want to do with faces? Well, there are an awful lot of things to do with faces. One is one would think in terms of better image features, more sophisticated probability models. We've actually fixed the named entity recognition thing. The slide is a little bit iffy. One might want to be able to do some sort of language thing with these faces. So my comment that Venezuelan President Hugo Chavez and Hugo Chavez are the same guy because they've got the same face, you could see doing a variety of quite congenial things with that observation. We've been looking at building a non-parametric face model to do animations out of this, because if you've got tons of pictures of an individual face, there's an opportunity to make some mischief, which is very tempting. And we've got, in fact, a very large and startlingly difficult face recognition data set out of this lot for free as well. So, in summary, there is a lot of partially supervised data out there. Generally, I haven't used the phrase partially supervised data yet, but you'll see everything I've talked about has been data sets where there's kind of an alignment between the pictures and the words, but I don't precisely know what it is. And it's a common thing particularly in vision, but I think more generally. Sort of like supervised data, but with a little bit missing. I've got a picture with a bunch of regions. I've got a bunch of words at the bottom. I don't know which goes with which, but I've got a huge scale. I've got a picture with a bunch of faces. I've got a bunch of names. I don't know which goes with which, but I've got a huge scale. Most of this kind of partial supervision involves missing correspondence information. What I'm going to be doing is something like linking and association. Common in the vision community, there are a lot of papers about this, are situations where the picture is labeled, but the object isn't segmented. Many people call this unsupervised learning of recognition. So I've got a stack of pictures of tigers, but I don't know where the tigers are in each picture. Lots of people have done some stuff. The thing that has amused me the most, to be honest, has been linking songs with album covers. There's a paper in NIPS about this. You can automatically predict album covers from short phrases of music. You can link words and metadata to pictures, and that's a problem that's worth doing. There are lots of cases where you can do it. The biggest case, I think, is this handwriting case. There's tons of handwriting stuff, and making it accessible is, in my opinion, a very big deal. I'm going to duck the coherence thing because this is mainly for the tracking community. Generally, when you run into missing data in these cases, it tends to be correspondence data. Okay, general conclusions. There's more data out there about the visual world than immediately meets the eye. You can see my prejudice. All of this is basically a vision talk for vision people, but with other stuff in it. Visual information should be linked with other forms of information, and doing so is really helpful. So you saw the amount of mileage we got from very simple natural language fiddling around with captions. It really helps if you have words associated with your pictures, and it may help on the word side. It's harder for me to be absolutely certain about that, because that's not really what I do. Actually working with these mixed data sets, with words, with pictures, and of course, by the way, when I say words and pictures, it's just what I've been doing, but there's video and speech, there's video and closed captioning, there's video and text, there's words, there's pictures and GPS. Choose one from column A and one from column B. Doing so seems to yield useful artifacts and insights into these data sets, and probably will teach us a fair amount about vision. And at that point, I'll stop. That's me. Mhm.
on the caption. Did you know, when you were doing the prediction, did you know how many pictures, how many faces were in the data set, or?
We knew how many faces the face detector had marked, right? The face detector we have, so one of the nice things about vision is we're really pretty good at face detection. We're not good at small faces and lateral views and the stuff, but we have taken the number of faces that the face detector found as being the number of faces that a caption writer looking at the picture would remark on. Now, one has to be a bit delicate here, but basically there are all sorts of weird features about news pictures and captions. The captions are highly stylized, and the pictures are as well. And if the caption writer looks at a picture, the faces they're going to talk about are the big ones that are frontal. And it turns out the big ones that are frontal are the ones we can really rely on detecting. So it's a reasonable step. Caption writers tend not to say, well, the tiny little guy on the third row over there is so-and-so. It's not really the way the business works. What that means also is moving out of the news domain is anybody's guess. I mean, it is a very structured domain, and it needs to be understood as that. A question?
Also on in and out, you mentioned the first name density in
Mhm.
is usually a
Mhm.
picture. What other textual features did you use?
Okay, so let me do two things. I'll expand on that first named entity thing. We built a rather cruddy but usable named entity recognizer with the following rule. We said, take the picture, take the caption, run along from the first site until you find a present tense verb. And if that is reasonable, regard it as a named entity. That works for about half of the caption. And then what you do is you take that set of strings and you just go string match them. And if you find, we built a named entity recognizer out of that. That was startlingly good. So these are very structured captions. What features did we use? We looked for commas nearby. We looked for parens nearby. We looked for open paren, capital R, close paren, open paren, capital L, close paren, and open paren, capital C, close paren, and sort of various variants of that. And we looked for where it was in the caption. We hadn't really gotten into the whole maximum entropy modeling bit. So we didn't rack up very large numbers of features because it was a nuisance. We've actually started trying that to see if we can get some mileage out of it. The biggest mistake, I think, was not looking for a short list of particular really indicative words nearby. I mean, words like shown, depicted, seen, that sort of thing. If they're right next to your named entity recognizer, they're a great big flag saying what's going on. Do I have a strong sense of what the best set of features to use is? No. I wouldn't, we haven't put an enormous amount of time into developing a set of features, not least because it's a sufficiently specialized domain that you wouldn't want to become the world expert on features to use in captions.
So, in the names and faces thing, there are lots of faces you eliminate.
Yes.
With the help of these clusters, can you go back and recluster them?
I think so. I hope so. So one of the things to notice is we have 500,000 pictures, but only 44,000 really big faces. Okay. What that means is we're being really conservative about which face detector responses we're using. We've done that basically because 44,000 faces is quite enough. You know, we sort of wanted to get on with it. One of the things I've been very keen to try and do is to go back to the smaller scale faces and to the poorer face detection results. The other thing that might strike people as being plausible to think about, and we're trying to figure out how to do, is pretend I can do in or out really well. Then I've got, in some sense, a kind of summary of the crimes of the face detector down there in the caption, and I should be able to use it. We don't know how to do that yet, but yes, that's a matter of real interest. So I should be, in some sense, I should be able to tune my face detector like this. We tried to build an unsupervised face detector and representer out of this lot, and it didn't work. But that could be ineptness as well as anything else. But I think it's really fruitful to go back and beat on the face detector based on what we've seen in the captions. We just haven't done it yet. Sorry.
Can you speculate on, besides faces, what else you can find in these pictures?
In the news, Well, I could speculate on almost anything, but the word speculate needs to be sort of underlined. And,
No, what else might work?
so the problem with the news is it's almost entirely about people. You don't see all that many elephants or whatever, right? People are really interesting, but they're hard. So one of the things that Jitendra Malik and one of his students has been doing has been, for the set of sports pictures in this news collection, saying, can we recover the configuration of the bodies depicted? So your typical sports picture consists of one or two people in weird poses across a baseball field or a basketball court or something, and they're doing this. It's not that easy to recover the configuration of the body because very often, firstly, the configuration is funny. Secondly, the pieces may have the same color as the background. There's all that other stuff. If you can get it, my guess is you can link it with verbs in the captions. We haven't been able to get it well enough to do that. Apart from that, you're almost certainly guaranteed to be locked into looking at interactions between people. So you might be looking at questions like, are these people shaking hands? Have I seen this person before? And the like. More general objects, there's just not much data in that data set. People are interesting. Remember, we can't, for most pictures, recover the configuration of the body. We don't know what people are doing in pictures. So it's, those are hard vision problems. Do I think that there will be much interaction between the language of the caption and the configuration of the body? My guess is probably not, but possibly. And the reason for that is that most of the terms that we use for the things that people do with their bodies, jumping, catching, throwing, that sort of thing, don't really constrain what you look like all that much. Most of these sports pictures, there's sort of arms and legs all over the place, and then there's a word there, but the word doesn't really constrain the configuration of the body. It could be very useful from the vision side, and the reason it could be very useful from the vision side is we don't know how to label pictures of body configurations. So it remains extremely difficult to take a picture or a movie of people moving and say, oh, they're doing that, they're doing that, they're doing that. And you could see a data set like this as maybe bearing on that issue. But that's still very speculative.
A variation on this in and out of the picture model. So you always allow for faces which are not, a name in the caption which doesn't show up as a face. How about the other way around, a face which doesn't show up in the caption? Perhaps, rather than doing open face recognition, limited to the kinds of people who are in have appeared with in other images.
That's tougher. And the reason it's tougher is you're basically saying, here's a face, and I don't have any information in the caption who it is. Let me figure out who it is. That really is face recognition. So one of the things that makes this stuff work is I don't really have to answer the question, who is this person? I have to answer the question, is this George Bush, Donald Rumsfeld, or Saddam Hussein? And that's a much, much easier question. What you're asking essentially says, can you answer who is this? And the answer right now for these kind of pictures is no.
No, in the open case, of course, it's very hard. What I'm thinking is that you have, 500 images with George Bush and other people.
Right.
And maybe this is somebody who appears like that guy, the bodyguard.
The bodyguard appears often. Now, the reason we get clobbered with that is people like Dr. Nakola. There are lots of people who appear, the fellow with the fork and the X-ray. There are lots of people who appear very, very seldom. And even and the co-occurrence statistics with people who appear often are not usually much of a guide to what they're up to. So I think what you're describing is about as hard as face recognition. And we've done several attempts to do face recognition on this data set. The thing about face recognition papers is you only get published if you claim about 95%. So everybody goes around shopping for data sets where they do well on. We were getting sort of 10 and 15% on this thing. It's a really, really hard data set because of the variations in appearance and color and facial configuration and all this other stuff. So my guess is it wouldn't work, but again, it's a speculation. I'm sorry, question?
What is the similarity measure between faces based on? I mean, is it, I don't know, is it a Fourier transform of it or?
So we did kernel principal components on the face.
What principle?
Kernel principal components on the face images, and then we took linear discriminants, so that set of kernel principal components. there is an interesting question lurking around in the background here, which is how do you do kernel principal components on 45,000 pictures? Because the kernel matrix is kind of chunky at that point. And you have to do a Nystrom approximation. You know the kernel matrix has very low rank. We then just racked up a bunch of linear discriminants and looked at distance in the linear discriminant space. It's a very crude representation. It's quite effective. And the reason it's quite effective, in my opinion, is we're doing something that's much easier than recognition. We really have to do, is this Bush, is this Rumsfeld, is this Hussein, not who is this? And there really is a very big difference between those two questions. We have tried much more sophisticated face representations for face recognition on the data set, i.e. you rectify the faces and you build deformable models to rectify the expression and rectify the color and stuff like that. And we still get very poor recognition performance. So, you know, my guess is that face representation is not as big a deal in getting the labeling right as the fact that the labeling problem is not that hard.
One more question. If you were completely unsupervised, that means
Right.
You would have pictures with captions,
Yes.
but not ever any prototype of anybody.
Right.
And would it converge?
So
You know what I mean?
I think I understand what you mean,
Some
but
pictures which would have only one name in it, but then most of the pictures would have several names, or at least several faces.
so let me read back to your question just to be sure. I think you're asking the following question. Assume that you have a stack of pictures with face detector responses and names attached.
Yes.
Does it converge? Right? Is that the
Yes,
question?
right.
The answer is yes, that's what we've done. We did not name any faces.
You didn't start.
No, we didn't start with named faces or anything.
Any
No,
seeds
no,
or any-
no seeds, no seeds. Right? So that's, my argument is that's an indication of how easy missing correspondence problems can be. Right? The missing correspondence looks like a nuisance, but it isn't. We're not using deep representations of the faces. We're not doing face recognition. What we have to do is knock off a correspondence problem that looks like maybe 1.5 to 2 bits per data item, and there's so much data there that those missing bits are not that big a deal. That I think is the right way to interpret it. But that's a useful phenomenon. I mean, as you've seen, we've done rather a lot of correspondence problems like this, and you can just brush this correspondence issue away, and it becomes helpful.
And would surveillance cameras be good enough, you know, to identify thieves?
When you usually...
This type of resolution and this type of...
so the issue isn't, the difficulty isn't resolution. The difficulty is essentially the entropy of the label you have to provide, right? Notice we're trying to crack a correspondence that looks like one face to maybe 3 or 4 names, a couple of bits. Surveillance cameras typically are saying, here's the guy with the gun behind the counter at, how many plausible people could there be with a gun behind the counter of the 7-Eleven? Well, you know, across the country in police records, there might be a couple of 100,000. It's a much, much harder problem, much, much harder problem. And it doesn't work. I mean, it's not known how to do that automatically. It's not the resolution of the camera. It's the representation of the face in the case of that problem.
The Hoffman's hierarchical model, is that the PLSA model?
Is that the PLSA model?
Is it the same Hoffman?
Yes, it's the same.
It's the same Huffman. It could be. I'm not that good with acronyms, to be honest. Maybe I'd have to sit down and take a look.
Well, the reason I ask is I'm told in text retrieval it doesn't work that well.
Oh, it's got all sorts of problems. It's got all sorts of problems. The document, it tends to overfit dramatically, and because of the document-specific probabilities. So there's a little bit of fancy footwork smoothing those. We didn't have major problems with it. So in the JMLR stuff, we fit an awful lot of different models. And, you know, there were differences between models, but not so that you'd stick a stake in the ground and say, well, this is the way to do it. And, you know, there's nothing there to say, well, don't do Hoffman. What we liked was the hope that you really would be able to split effects between very general effects and very specific effects. And, you know, that seems like a good thing to try when you browse. We didn't have too much trouble with the overfitting. It has a nasty reputation for overfitting. We didn't seem to have too much trouble. I think Mrs. Bly and Jordan have fiddled around with it a little bit to change the document-specific probabilities. That's what the latent directly allocation stuff is about, and that's supposed to be better behaved. And there's so many of these things, it's very difficult to be sure who's best. Sure.